So, we are sorry for that. We are going to start again the presentation. I don't know if you can hear me now. I'm going to try to show, yeah. But okay, if not, we can, I don't know, do something to have a similar version on the cloud or whatever. I don't know. So now I'm going to reintroduce the topic. So I work in neural network explainability and interpretability. So what we are going to do today is to try to use topological methods to understand how well a neural network can generalize. How well a neural network can generalize. So let's go ahead. So the first question will be, if I give you these two models, which one is better? Someone can answer that? Which model should be better? This is a transformer, this one is a transformer, and this one is a simply multilayer perceptron. So, in principle, what we will say probably is that this model will be better because I mean it's a transformer, it uses attention methods, etc. So it's better developed or whatever, no? And this will be the naive answer for that. The question is that there are some theorems that say that any multilayer perceptron like this one, this simple thing, can approximate any continuous function. And this is nice because if we, with a big enough number of neurons in the neural network. So this is nice, but it handle a problem, no? Because the thing is, how can we compare these two models if I know that I can approximate whatever thing I want to approximate with this one? How can I say this one is better than this one, or this one is better than this one? This is difficult because it doesn't depend only on the architecture of the network, but also on the data and also on the number of neurons. So a way to do that is a classical measure to compare neural networks with accuracy when we talk about classification. And we are going to talk about classification during the whole presentation. The classification problem is you have some inputs and you want to assign a label to each input. For example, you have images of dogs, cats, whatever. You want to get a photo of a cat and you want to classify correctly this photo as a cat. So a way to see if a neural network is trained properly and works properly in a dataset is to split your dataset in two, in train and test, and then in the test with the train set you train your network, and with the test set obviously you check if your model generalizes properly. So this is a measure with accuracy. Accuracy is the number of predictions in the test set that are doing the ratio of good predictions on the test set. But this is what I have said. Everything is done generally with the test set. You can perform accuracy wherever you want. You have a data set, you can perform the accuracy on this data set. But we usually use the text data set. But nowadays we use also the generalization gap. This measure is important because we don't always want only to test with the test set, but we want to see what are the differences between the performance in training and the performance in test. So what we do is, okay, let's compare both accuracies. And so we define the generalization gap, that is this measure based on the training and the test sets for a model M, that is the accuracy of the training in the model M minus the accuracy of the test in the model M. So this means that the lower is this number, by the way, it can be negative, the better. Because we are saying that, the test accuracy is near the training set. And we know that in actual models, what we get always is nice results on training because we can overfit. So we want to assess that we are not memorizing data. So comparing generalization gap is a usual way, it's a nice way to compare two models. So we have one model, the transformer, another model, the MLP, for example, and then we can numerically compare both models with specific values for the parameters that we have learned, and also with the data set that we want to try. And this is nice because also, if you have this, and if you can predict this number using only the train set, then you can get the accuracy of the test. So what we are going to try is to predict this using only this, the train set. Okay. So this is the outline that we are going to do today. First, we are going to talk about computational graphs and neural networks. And then we will define these objects that are the network dynamic matrices These matrices are the ones that we are going to use to apply TDI on them. Later on, when we define that and we define the theory of that, it will be brief. Then we will go to neural network generalization lab prediction using these tools of TDA. And then we are going to talk about conclusions and future work. Like this is absolutely no. So let's start with computational graphs and neural networks. So the first thing is that you can define, I don't know if you have read books about deep learning, theoretical deep learning, but a lot of books have a lack of definition of what a neural network is. So there is a theory, a machine learning theory, practitioners define computational graphs and then define neural networks from these computational graphs. So a neural network in particular is a type of computational graph. So let's define what is a computational graph and then a neural network. So a computational graph is only a function, and whatever function you want to take represented by a directed graph whose non-input nodes represent functions and the connection between functions, no computation of functions. Later we will see a photo of that and we will work on some examples. So the thing is that, for example, it's not represented. Okay. So imagine that we are saying that its non-input node is a function and its input node is a value that you give to the network to compute the other value. So what we are saying is that if we have a, can you see the blackboard in house? Well, the thing is that this, if we have, for example, three input values of the computational graph, the value here, this will be a function f, depending on the values of this, and this. But also, if I put here another one, we can do that. So, if we have a function f, a function of ABC, and we have here a function of g, this function g will depend on the output of f plus c. And we can define complex functions iteratively with these flags. So yeah, if we give a value for the inputs, we get a value on all the nodes of the graph. And also, we call output nodes to the nodes that has out degree 0. So it has no connections to other nodes. So every arrow to this node is pointing to this node. So these values will be the output, no? And this is a nice example of this computational graph. No, we can define, for example, an input node that works on vectors, for example, the vector x. Then we can define another input node that works on matrices, another one on vectors, and another one on vectors. So as this one has in degree 0, because it has no incoming arrows, are the input nodes. We will put values here to compute values on the other nodes. And the output values will be the values in which we are interested, the output of the function. So we have a function, for example, it will be a function of, I don't know, 1, 2, 3, 4, a space of 4 A, B, C, D, and we go to another space E, for example. No? So, for example, this one. This non-input function has this non-input node has the function f of u that transposes a vector. This one takes two matrices and multiplies the matrices. This one multiplies a matrix with a vector, and this one sums x, y, and z. And if we start by computing every function with these inputs, we will get for output this f, x, y, z. So, in particular, neural networks are computational graphs. So, because they have an architecture, they have an input values, input nodes, and they have output nodes. So, for example, in classification, what we have as output nodes will be the, well, I mean, we will have output nodes in general, one node per class in the classification problem. And as the input, we will have the values that we will feed to the neural network to predict a value for a class. And in fact, we also, in general, we ask for the neural network to be, well, the functions of the neural network in the non-input nodes to be almost everywhere differentiable functions. Like, for example, the 25 linear units. This is a non-activation function. So, in general, this is the maximum between 0 and x. And this is the variable everywhere except for 0. So, we more or less we ask these properties, and then we use these properties to define the gradient and then to optimize the parameters of a neural network. A neural network again has input non-input nodes that has parameters that we want to learn. But computational graphs are not neural networks. Neural networks are a subclass of computational graphs, and this is nice because there are other people out there that are working with computational graph theory to prove things. For example, if we instead of having as input values of Rn or whatever, we can put probability density functions of probability density functions of probabilistic spaces. And if we do that, we can in some way check properties of these probabilistic functions. For example, if they are trapped, the integral are trapped extractable or not, using only the properties of the composition of functions. And this is nice because in fact, 1 year ago, one team published a paper in the previous release where they proved a classical conjecture or about tractability of probability functions using these things, and it was considered a major step. So, in general, what we are going to define is a framework to analyze computational graph, any kind of computational graph. So let's now define or matrices. No. So now we have this object that is a computational graph, and now we want to extract something that we are going to use to give interpretability of neural networks. And these things will be matrices because we can analyze the iterations of a matrix. And this is nice because, as in the first thing we were explaining, what we usually in GPA is to take a point cloud. No? Take a point cloud, we take a distance between points. And this is nice, but what we can do also is to define the distance matrix of this point cloud. And then we can analyze directly the TDA of a matrix. And this is another major step, I think, that we are going to do. But let's define these matrices. So first, let's take any neural network. For example, let's take a very easy neural network. Like, I don't know, this one. And fully connected, okay? What we're going to do is, and we will have a data set, the typical data set of images, I don't know, of 3 vectors, no? We can have, for example, 3, 5, 3, 2, 4, 2, whatever. A data set of m values. So what we're going to do is to compute the function values of each neuron here, okay? Except the input one, because the input ones are these ones, and we are not going to analyze the input because we are not interested in that. So what we are going to do is feed that in here. For example, if we say that this is input that takes this one, this takes this one, and this takes this one, we feed here the numbers, and then we compute the value. So for each neuron, we are going to define a vector that will contain all the outputs for all the possible inputs. So if we have n examples and n neurons in this part, then we will have vectors in, and assuming that every function is like this one that takes a value in Rm and takes an output in R1 and in R, we are going to have vectors in Rm where each component will be an output value for one of the examples. Okay, and this will be point clouds in general. So then we can define the point cloud as these vectors in Rm. And then with the point cloud, we need to give a distance function. So here, there are a lot of ways to give a distance for a point cloud. We can give the usual Euclidean one, we can do whatever. But what we are going to do is to try to find a distance that gives us information about the neural network. We will see that in the future, but let's select a distance, an arbitrary metric, d. So what we are going to do is to compute the distance matrix of this point cloud, and then we will define this distance matrix as the network dynamic matrix of this dataset and this computational graph. Okay? So also, if we do that, it's obvious that we can, instead of using the whole dataset and the whole neural network, we can sample the number of neurons and sample the number of inputs that we want to use. Because when we talk about neural networks, we are talking about millions of parameters, millions of neurons. So we can so that because the TDA usual algorithm is of order cubic order. Okay, so we need to avoid using millions of neurons. So this is more or less what we are going to do in a better way than in the blackboard. So we will start with a training data set, for example, images and images. Then we are going to feed our neural networks with these images, and we are going to take per each input a value in each neuron. And then per each neuron, we are going to go to a point in Rm where each point will have the coordinates of, will have the output activations for each of the examples. And then we will have this point cloud that we were setting. Then we can perform sampling if we want, and then we can compute the distance matrix. This is the whole pipeline to compute these matrices, and this is a very nice way to see it. So now, we are going to use this because we are not only defining theoretical things. We are going to use that to give interpretability, or more or less, because this is another important. So let's give a little context of why interpretability and explainability matter. So in the last months and years, especially months, there's an increasing interest on this topic, no? Because now there are a lot of neural network architectures, we don't know which one we want to use. In fact, even businesses like companies, important companies are working on that because they have like hundreds of models and they want to select the best one. But how? Because yeah, you have a test set, but this test set, sorry. I mean, if you take a test set and compute accuracy, you are losing part of the information of the data set. So what you want to do is to avoid this split in two, and you want to give or to see what is happening in the network. So we are going to try to give some insights on that. So in particular, many papers in the last year have been released, trying to predict the generalization that we have seen before. In fact, some of them use basic TTA for neural network interpretability. So, in fact, there are two important things that have been done. One of them is to study. Okay, so let's define what is a layer of a neural network. So a layer is, let's not do that, but no, because not only I need to go inside. But the thing is that every time we go from the input to the next layer of neurons, so the neurons that are at distance ones of the inputs, we call this a layer, okay? And then we can talk about the first layer, the second layer, the third layer in relation to the number of the distance to the inputs of these neurons, no? Or the minimum distance. We get mathematics more formal. But if we analyze the topology of the inputs, going across all the transformations, what has been proved is that what neural networks are doing is to reduce the complexity of the space of the point. So if you take a data set and you start going layer to layer, each layer transforms the point into a space that has less holes, topologically speaking. And this is nice because this was used to give interpretability. Because the neural network that has a better, more fast decreasing of number of holes were better than the other ones. So this was one approach. But there are a lot of approaches. Also, they analyze this space of parameters instead of all neurons and the output. We analyze only the parameters of the functions, and this can be done through neural networks. But the problem is that these nonlinear functions are important in neural networks because they give behavior to the network. So in 2020, we promoted a challenge where the goal was to predict the decision gap of a whole set of neural networks for the same data set, and to order these neural networks by their performance on accuracy, but without having the test set. In 2019 and 2020, the Ciprian, or mate, published two papers using this approach but not defined formally. And he proved that with this distance between neurons, the correlation between neurons, he was able to recover information about the decision gap of basic networks of the order of thousands of neurons. And this was nice because this was the first proof that we were able to predict the decision gap using this topology. So also, the advantage of these papers were, well, it was mainly one, and it was that it takes into account the nonlinear functions because because if you analyze only the parameters of the neural networks, you are lacking information. Because the topology for two completely different outputs, because you can put, for example, a sigma or a ReLU function as nonlinear activation, will give the same topology. But this is not true because one network can go very better than the other one. So we need to take into account the nonlinear functions on each node. So the advantage of this paper was specifically this, the definition of the network distance matrix that we are defining formally. So our main objective was to generalize and formalize the methods of this paper and to, when we say generalize, we talk about giving this algorithm a way to compute the decision gap for big and big networks, doing something in particular. So let's state the problem that we solved in this project. So given a task T, a task is only a set, a data set, a fixed data set of images. We will see which ones, and a set of neural networks that are divided into training neural networks and test neural networks. What this means? This means that we are going to train a linear model with one set of neural networks, and with the other set of neural networks, we are going to try to predict the decision gap of these neural networks using the linear model trained with the training data set of neural networks. This is a little bit different from what we are used to do, because what we are used to do is to split the data set and to have only one neural network. Now, what we have is several neural networks, and we want to predict the decision of these neural networks. So the real data set are the neural networks. So we work with two different data sets. The first task was has a data set, the DC5, that are images classified in several, in particular in 10 different labels, airplane, automobile, etc., with 96 BCG-like neural networks, convolutional neural networks. Instead of learning functions for each node, we learn only as parameter a filter. And on the other one, this is a street view house number. Here we have plot images of numbers in the street that we want to recognize. To recognize it, for example, a 2 appears here in this image. No? So in order to do that, we are provided with 54 CNN neural networks. I'm not going to explain what is this, but this is networking network architecture. I'm not going to explain it because I don't know exactly how this works. But the important thing is that we can apply this algorithm to this network. So we want to learn a linear model. E equal to mx plus n, where E will be some feature vector related with our neural network, and in particular will be one persistence summary, topological summary, as we saw in the first seminar. So in the first seminar, we saw how to compute from point clouds persistence diagrams. So instead of using this point clouds, we are going to use distance matrix, but it's exactly the same. And with these tools, well, I mean, we can compute persistence diagrams, no? So what we have is for each neural network, we have persistence diagram. Compute on the training dataset of the far or whatever, okay? So we have the training dataset, we compute our network distance matrix with the training part of this dataset, and then we compute this matrix, and we have a matrix for neural network. So what we need is to vectorize these persistence diagrams and to fit them into the linear model. And that's all. We saw many ways to do that, this vectorization part. In particular, we are going to work, well, what we saw is that the best ones are the ones studying the distributions of the points in the persistence diagram when we model it. So if our persistence diagram is something like that, we have a lot of points here. The idea is to study what is the distribution that more or less is approximating these points in the persistence diagram. And what I mean with these quantities, we obtain very nice results. So the pipeline again, with the images, we have the training dataset with some examples. We have a neural network, we extract the distance metrics, this network dynamic metrics, then we compute the persistence diagram, and then we get topological summaries. Okay? So, the general pipeline. We have a common dataset, CFAR or street view house number. We have k different neural networks. We compute from the previous pipeline one topological summary, the average of births of death or whatever standard deviation, for each of these networks. Then we split into the set and training sets. These things are a new data set. We split it train and test, and with the train we feed a new linear regression with this. And then with that we try to predict the generalization gap. So obviously, in order to do that, we needed to sample the number of neurons and the number of elements in the data set because the data sets were huge and the neural networks were huge in the number of neurons. So for the data set sampling, we use a uniform random sampling. Okay, we just take whatever. And for the neurons, our strategy was to sample the ones with more neuron in the parameters, in the linear fashion. So, okay, Google Challenge had 3 winners. So we compare with them. No? How do we compare that? So we do the same for them. We feed a linear model for part of the network, and we try to predict the decision gap using their methods with a linear model in order to see if they are also correlated. So what is confused here is the Pearson correlation between our predictions and the real precision gaps. So what we see here is that these are the 3 things that won the Google Challenge, and for that one, that is the one with images, with random labels of images, we obtained the second best performance predicting generalization gap with this pipeline, with this linear model. And the one that won in this task was this one, and they obtained a very nice result too. But if you see here in task 2, this winner, it's not the winner now, but also is worse than our method. And also, the better here is the worst in the first time. So what we achieve here is that a consistent method to predict the decision gap, and more or less state-of-the-art results, but stable, because here they are not stable. When rain was. So we can also observe differences in the persistence diagrams for the neural networks. Here we have in the first row we have one persistence diagram for dimension 0 and 1 for both tasks of the base network or with the network or the network with base generalization with highest generalization gap. And in the lower row we have the other ones, the ones that has lower generalization gap. And just here, there are a lot of differences. So for example, look at the dimension 0 points. Here, they are that here in near 0.5, but here we have more points here. And in fact, in dimension 1, this is even clearer. Here we can see a difference between persistence diagrams. And also here we can see a difference between persistence diagrams and also here. But in fact, if you look at that, this one seems this one, and this one seems this one. So it seems that the relation is inverse. This is another point. We need to study this here. But if we plot the generalization gap, for example, we have as the x-axis the standard deviation of text for each of the persistence diagrams for the worst neural networks and the best neural networks. We see, for the task 1 neural networks and the task 2 neural networks, we see that more or less the generalization gap follows a linear trend, no? With respect to these topological features. These are, the standard deviation of text, there, etc. And in fact, except this one and this one that are very different, here we see the same trend in both tasks. So what we have seen here that seems contradictory, here it's not that contradictory. So we need to study this. But well, we see this direct relation between. So if we assume that this works, there is a new and finishing. There is a new field in mathematics and GPA that is differential persistence diagrams. And in fact, let's take any point now, any point like this one. And let's see what happens if we try using the gradient descent. You know what is gradient descent? It's only to try to minimize one function. We use the derivatives of the function. So if you have as function the sum of persistence of points in the persistence diagram, so for example, if you want to have your persistence diagram. Yeah. and you try to minimize the distance with all the points and the diagonal, what you get is this in dimension one. Look at the train. Look what are the points doing. So they are generating cycles, in fact. This is, I mean, I don't know what you think about that. I think it's amazing because this is the proof that we can use TDA to tune networks. Because if networks are related to TDA in some way, as we saw, we can use this method to obtain what we want, lower standard deviations or lower whatever. Whatever thing that is differentiable is a composition with a persistence diagram function. And this is nice because what I mean, this is going to continue. So let's conclude. The first thing that we have seen is that these topological features of the network diagram matrices are able to distinguish more or less between good and bad neural networks with respect to the decision value. Also, this somewhat implies that topology is playing a crucial role when designing and training neural network. And this is nice because this is not only proven by us, but also with other people looking at the evolution of the TDA when to go from one layer to another layer. Also, this procedure can be extended to any model that can be expressed as a computational graph, not only neural network. And this is nice because, for example, if you design something with a computational graph like a probability distribution, you can study more or less in some way the properties of the topology in this space. But the worst point here is that first, this distance is horrible because this is not a distance, this is not a metric. So in some way you need first, the first thing is that this only captures linear correlation because this correlation is the Pearson correlation. So when we try to match neurons and define their distance between them as the correlation, we need to look at more flexible correlation, not only linear. So this must be avoided in the next course. But also this is not a metric. So this is even worse because stability theorems do not hold. At least this is what we think, but in fact, we are proving that in fact they hold more or less. Also, architecture is not taken into account because what we are doing is discarding all this information and putting everything in a point cloud. The sampling methods must be improved because when sampling neurons by the norm of this the parameters must be improved because this does not give any information about the neural network in principle. You are only saying, okay, take the ones that give more output values and that excites more the network. This must be improved. But it works. It works. And this procedure depends on a dataset of neural network because now we are training linear models from a dataset of neural networks. So we need a way to avoid this and to get a universal description of neural networks using TDA. And this is part of our current advance in this one. So this is everything, I think.
Thank you, Gwen. If you have any questions, I will pass on the mic because otherwise I don't think that they will hear you at home. So if you have any questions, also if you have any questions at home and you don't want to speak, you can speak. But if you want to speak, if you don't want to speak, you can write in the chat and I will read them. So if there are any questions. But I will start with the question, okay, if that's fine for you. Yeah, I wanted to ask you, and this is out of curiosity, but since you talked about interpretability and explainability, I would like to ask you two things actually about this. One of them is, okay, so you learned about the generalization gap, but could you explain to us what the information about the generalization gap is given to you? I guess because the problem with neural networks typically is I don't know exactly what is learning, and I don't know, well, I know how it is learning, but I don't know exactly what it's learning. So I don't know if it's taking some extreme relationships. I always explain the same idea, the same example to everyone. No? The example with if you have some noisy images because you are taking medical images from a noisy machine, then it will take the noise in that machine and you are not able to see it, whether the neural network is. So we are always trying to avoid this kind of stuff, and interpretability and explainability is trying to erase this kind of stuff. So with the generalization lab, what are you learning about that? So what kind of information does it give you about neural network and the data set and what is learning? This is one question. And the other one is, have you performed visualizations? Because I think it's super interesting, not to see, to maybe study the space of neural network and no, and if you are trying, if you are dealing with TDA, then you can perform visualizations and you can define things theoretically.
So these two questions are very good questions. Let me answer first the second one. We have performed some visualization, but on the output of the source, like the one that I showed you. So when you lab, okay, let's see how this topological summary relates to your decision path. But we haven't done any visualization on this spatial matrix. This is in fact something very new, so we can't work on that yet. And for the other question, this is an initial work in progress, because in fact, one of the things that we wanted to do with this neural interpretability was to study these resistance diagrams of the network, but when fitting with adversarial examples. So we are trying to see what is happening there. But nowadays, what we know, or more or less we interpret from that, is that, for example, when you go to here, no? In dimension 0, you have these differences of text of the points. And this is nice because in some way you can interpret these dimension 0 as connected components. The connected components, based on the correlation, are giving us information about nodes that are related in the activation process. So, for example, if you have more neurons that are very correlated, so they are learning more or less the same information, they will generate faster cycles. So, sorry, they will, the cycles will die before. So, more or less, you can try to relate this relationship between how neurons activate values using this, but we need to work a little bit on that, because what Sergio said some time ago when I started, and we need to visit this, is that neural networks that are memorizing tends to have this form, and the ones that are not memorizing are taking this form because they have different activation. But in fact, the problem here is that we are looking only at the activation. So more things might not. In fact, I think this is a personal opinion, but this is not true, or we don't know if it's true, that these differences here are because we are using a very strict correlation. So when we analyze the components, connected components, when we do the filtration, I think we are being too frustrated. But I don't know, this is only a guess. So this is we need to work on that.
Okay, so another question, because I find it very interesting. I don't know anything about predicting the generalization gap. So could you explain, if you know it, and a bit of your opinion? I don't need it to be too fast, but could you explain maybe a bit of what has been done to predict the generalization gap? So now you have explained this, and I cannot imagine another way of doing it, right? But what other ways have been applied, if you know them, to compute the generalization gap? And what do you think that TDA offers extra? I mean, if you're improving and it's more stable, then of course it's better. But what do you think that can be learned with TDA that has not been learned with the other?
Okay. So what is being doing? There are a lot of things that are being done right now in interpretability, but the most important thing in this area, I think, is the data augmentation. Because when you do data augmentation, you can get like that data set that it is not it comes from the train set, but in some ways not equal to the train set. So more or less, you can try your accuracy of this new set, and this will approximate if you have a very nice data augmentation process, will predict in some way this application.
And maybe like cheating.
Yeah, it's cheating.
It's like
exactly
applying it to the test.
I wouldn't say that well, the company will maybe he will sorry, they will ban this behavior because it's cheating. But other things, for example, you know that at the end, what neural networks are doing is to take your inputs, okay, putting a separator, for example, no? So one other thing that people do is to compute, okay, the point from the different data sets, sorry, for the different inputs from through values, they compute the distance with the separator. And the bigger this distance is, the more are the better are working this method. Because I mean, if you put your separator here, this is clearly a separator of these two data. But if you have, for example, something here, the separator is here, it's not working more a problem. This is in more dimension than this. Obviously, this is a very nice separator, but this is a thing that is being done actually. With TDA, I mean, I think TDA allows us to focus on the shape of the architecture. I think this is the most important thing of TDA because you're not going to understand anything as an isolated. What you want to do is, like, in my opinion, is to give a general behavior of the network. You don't care if the network is doing something special in this, well, maybe yeah, because there are certain effects. But in general, what you want to do in a general context is to study the global behavior. And what you know is that topology in some way, when you do this space and you do these things, is trying to study that, this global behavior. But I mean, it's not fantastic because there are a lot of things here. Maybe one neuron is affecting a lot the whole neural network, and then you need to take into account this, but you are sampling. So how can you assure that you are not missing any information on this TDA? So this is another thing. We need better knowledge. Some people, what are doing some people now is to study especially the input. Because okay, look at that. If you have your input and your separator is like this. So for example, imagine that you have a data set, whatever, okay? And your neural network is predicting, I don't know, like that. These are inputs and the cycles are one class and these other are another class. So here, this operator is easier or more difficult than this one. Obviously, this one has a hole and this one has no hole. Obviously, this is a very reduced and naive interpretation, but if you have big and big separation separation lines, whatever, I don't know how they call that. The thing is that if you try with topology to reduce with this dimensionality results to avoid many holes, what you can get is better separation functions. And this is nice because you can study it. And this is another thing that is being done now. I think what they are trying to do is to reduce the number of holes. And this is working, and this works, and it has been proved that topology losses of in the gradient descent, if you put losses that takes into account the number of holes in the input that generates the predictions, you are going to get better networks in general. It's a good representative. So I think in some way what you want to do is to study the global process. And I think topology can help here. I don't know.
Okay, so this would be the last question for me, Joanne, if you want to answer questions. Yeah, I wanted to ask you, since you're doing this, you are studying the topology of the neural networks. So, and just, you can tell me your opinions, basically, like you cited in papers, but what do you think that this would be also interesting for? So, let me explain. What do you think that this study would also create? Also, where would you apply also this study of the topology of the neural network? Because I wanted to ask you because, for example, in this room, anyway, in the seminar room, it has appeared many times the term of differential privacy and so on. So, for example, do you think that this could be applied maybe to the fact that if you have, what you wanted to do, more or less, if you want to apply this to model, like you want to prescribe communities, or if you take your model to another hospital and so on. Just your thoughts about all this.
So this is not a very interesting question, because what we are doing here is to bring the internalization gap without the test set. So we are like getting bigger data sets for training neural networks. So what we can do with this project, for example, is as simple as, okay, let's put more data into the training page. This is nice because if you are trying to decide which model is better, you usually take your train set, your cross data set, or whatever, in order to validation data set and then the test set. You are like doing a lot of split and losing a lot of data to train models. So a nice thing that you can do is if you need to go to an hospital and you need to take data and you need to train models there, because this is what happens actually currently, it's better to have more data. And this is a way to compare neural networks or compare different implementations without taking the risk of losing nice data. Because, for example, in hospitals, there is, I think, I don't know if someone is to me now, and this is false, but I think that there are some labels in this clinical machine learning that are very scarce to find. So if you need some of them in order to have a nice data set, you are losing information to training set. So the idea is not to lose this important information, because there are diseases, whatever, and you need all the information. And you don't want to lose the information in the test set, only for validating your model. And the other thing is that, well, obviously this can be used, if this works at the end, this can be used for AutoML. So you start generating random models and you start training them, and then automatically you can take the best one. This can be done in other ways, but this is a nice way to see it. And this was, in fact, the first thing I wanted to do. For differential, I don't know, because we were talking about a lot of things. Not about differentiability, but in some way, well, I don't know, my thoughts are that this is only for model interpretation, but this book is not that used for it.
Well, I don't know if the people at home want to ask something, because you have them quite big.
Can you hear people who are not in the room?
Yes, we hear you.
Ah, okay, excellent. Then maybe I can also ask a couple of questions. Ruben, can you show again that slide with the results of the Google competition?
Yeah, this one.
So those R-square values, they refer to a linear model. What are the variables of this linear model?
Yeah, the vectorization that we get from the persistence diagram. So, for example, your input for the standard deviation model will be the standard deviation of the beds and of the beds of dimension 0 or dimension 1 or whatever dimension you want that is. I mean, you are regressing over this standard deviation of beds and beds. In particular, in the visual, because where the best one for us. But in general, what you put is a vectorization of the persistence diagram. And in particular, this is one of the there are a lot of ways to vectorize that persistence diagram. In fact, this is the thing that is. I don't know if I have answered you.
But yeah, so R-square, it refers to a regression that before you wrote y equals mx plus n. So I understand that y is the generalization gap.
Yeah.
And what is x? I think, did you choose a single topology descriptor or a combination of them? So what was the x which produced precisely those R-square values that you were showing us?
Yeah, so we put a lot of combinations between persistence entropies, persistence, some vectorization of landscapes. We use also these standard deviations, and we use a lot of mixed models, but the ones that were the best for us were the ones that were only with standard deviations in dimension 0 or 1. So the input was a concatenation of the vectors of the standard deviations and averages for the depth and depth in both dimensions. So 2, 4, 8 values. And this was the best model for both tasks in particular.
But with the same combination of persistent scriptures, task 1 and task 2.
Exactly.
Okay, thank you. And just for curiosity, what did the other competitors do? Because if they also give R² values, it means that they also took a linear model y equals mx plus n. So what was the x for them?
No, not exactly. It was not in this way. They give what they give in the model is a number that tries to, well, I mean, it's more or less, I don't remember that because this was 1 year ago and I don't remember what they are doing exactly. I think one is using this marginal gap between the separation functions and the data set, but I don't remember exactly what they did in these methods. So
how do they obtain an R² value?
No, we obtain the R² value. So
so those R² values, it's you who computed them. Okay, that's clear.
Exactly, compute the model. So what we did is to split into neural networks for training, neural networks for test, and we use the methods to predict the decision gap. We train a model with these values that they give us, and then we perform the RSO. But we also train with the output and another model for each of the things. Yeah.
So then, when Google decided who won the competition, what kind of values they took into account? Only accuracy or what?
Yeah, they did more or less a challenge. What they wanted to do is, okay, I have this test data set of neural networks, and what we want is to order the neural networks by the accuracy or the decision gap. No? So instead of predicting, they wanted only to order by the decision gap. So this is an easier question than predict. Because, I mean, if you, for example, have 2 neural networks, you put the best one as with a value that is higher than the other one, so the models are saying, okay, the ones with higher value in the output are the best ones. So you order by these values. So they are ordering. They only want an order of the neural networks. And this is what.
Okay, thank you. I have more questions, but I will ask you privately. So I'll let other people talk.
So I don't know if you have more questions or no.
Maybe somehow you should try to convince the audience that this is a useful tool for their studies. So I think I already asked you why this can be useful to them. You said that it can increase, so to say, the size of the data because you can save the test set. Is this the only way in which it can be useful?
No, there are a lot of ways. I mean, for example, one of these is one. Another one, I mean, for example, you want to, I mean, we need to think about that. But one of the simple things is to design better models and to do automatic learning on the site, because you need to go there and you need to work there. So you can try to have an automated model that doesn't need, for example, a person working on this. So, for example, if you can go to a hospital and you can run a program there, you can run this automatic learning program and it can work without the supervision of anyone. So this allows people to train better networks without looking at the model. So because if you need a person that goes to the hospital and look at the values of the neural networks and then start another training process or whatever, this will take time because you need to go, you need to check values. If you let an application to do that automatically, you can get at the end a very better model because it's working all the time. So this is one thing. Other thing is that, okay, also we can get more information about the data because we are not understanding this kind of information. And also, this is not exactly the same, but with the data, at the end, the good thing here is that we are giving a way to compare matrix distance. So in some way, if we can get information about the data we are working with, and we can give a distance between data, we can also check if the data is more or less aligned in value and information. Because, for example, if you have the other day, they were showing us this mammography data set, no? And they were saying that, for example, in some places, this information was worse, and in other places they were better because or had different information because different people were labeling the data. So one thing that you can do with that is to try to normalize these data sets and to extract useful information with the distance matrices. And in order to do that, I don't know, this is only an idea, but maybe you can get some distance between data sets, a distance that is not too restricted to the context, but that has some information, and they compute what we are doing, this TDA. But I mean, this is only TDA. This is not exactly with rate recognition. I think that this work nowadays allows to auto-training of neural networks and to discovering of better models without the supervision of people, like in a unsupervised manner. That is some of the goals of the neural networks today, to be trained automatically.
Okay, thank you.
Well, if there are not any more questions, then this would be everything. So thank you again for Good morning. I will probably stop the Zoom, but you are encouraged to talk into this committee if you want. We have a little bit of time, so I will stop the recording if I go out.